Hello, in this video we're going to go over the classification of alcohols as well as their physical properties. Alright, so we can classify alcohols into three categories: primary, secondary, and tertiary. Now, these categories actually depend on the carbon that OH is bonded to. So, for example, down below, if the OH group is bonded to a carbon that is only bonded to one other carbon group, then we call that a primary alcohol. Now, if your OH group is bonded to a carbon that's then bonded to two other alkyl groups, then that's called a secondary alcohol. And then finally, if your OH group is bonded to a carbon that's bonded to three other alkyl groups, then that's called a tertiary alcohol. And some examples are given down below. So for a primary alcohol, one example is 1-propanol. So notice that the alcohol is on the very end here, and then the carbon that it's attached to only has one other alkyl group attached. So there's just a single chain of carbons. There isn't any branching. Now for secondary alcohols, let's look at the example down below. We've got our OH group, and that's bonded to a carbon that's bonded to two other carbons. So there is some branching there, and this is 2-propanol. Okay, now in our last example, we have our OH group, and that's bonded to a carbon that is bonded to three other carbons. So that would be a tertiary alcohol, and this molecule is called 2-methyl-2-propanol. So let's look at some more examples and see if you can figure out if these are primary, secondary, or tertiary alcohols. And actually, I'm going to draw some examples that we saw when we were naming alcohols. So these might look familiar. Okay, there's that one, which we said was called 2-methyl-1-butanol. Let's also look at this example down below. This one we said was called 4-methyl-2-pentanol. And let's just look at one more. I'll just add another one in here. All right, so see if you can figure out whether these are primary, secondary, or tertiary alcohols. They might all be different, or they might all be the same, who knows? But you can pause the video, and when you come back, we'll go over them together. Okay, let's start with the first one on the top. Is that a primary, secondary, or tertiary alcohol? Okay, so the first thing I'm going to do is locate the carbon that the OH group is attached to. So that's this carbon here. And then I'm going to count how many other carbons that one is bonded to. So it's directly bonded to this carbon. So there's only one carbon that our carbon of interest is bonded to. So this would be a primary alcohol. So there's only one alkyl group attached. Okay, let's look at the second one. So let's find the carbon that the OH group is bonded to. And let's count how many other carbons this carbon is bonded to. So it's bonded to one on the left and one on the right. So that's a total of 2, which means we have a secondary alcohol. And then let's look at the last one. So let's find the carbon that the alcohol is bonded to. And how many carbons is that carbon bonded to? 1, 2, 3. So this is a tertiary alcohol. Now you might be wondering, why do we care? Why are we classifying all of these alcohols? This is going to be important when we start talking about alcohol reactions. So for instance, primary and secondary alcohols might produce one type of product, and tertiary alcohols might produce a completely different type of product. So when we start talking about reactions, this will be really important because you'll need to be able to identify whether you have a primary, secondary, or tertiary alcohol in order to predict the product you would get. Okay, so that does have a purpose. I'm not just trying to torture you. Okay, now let's talk about some physical properties of alcohols. So one difference with alcohols compared to alkanes and alkenes, for instance, is that it does have, or all alcohols, have an OH group. And you might remember from Chem 121 or other chemistry courses that the OH group is polar and it's capable of an intermolecular force called hydrogen bonding. So this hydrogen bonding makes low molecular weight alcohols highly soluble in water. So let's look down below. We have the molecule methanol, which just has a CH3 group attached to OH. And there's a second one over here, and this is dissolved in water. So we also have some water molecules as well. And let's just kind of label these so we can keep track. But remember, in hydrogen bonding, if you have a hydrogen bonded to either nitrogen, oxygen, or fluorine, that has the potential to hydrogen bond. Now, hydrogen bonding has to occur between the hydrogen on one molecule that's either attached to oxygen, nitrogen, or fluorine, and the oxygen, nitrogen, or fluorine of another molecule. So notice here that we always have a hydrogen between two oxygens, at least in this example. So those are hydrogen bonds that I just highlighted. One easy way to remember the atoms for hydrogen bonding is hold the phone. F-O-N. So again, if you have a hydrogen bonded to fluorine, oxygen, or nitrogen, it is capable of hydrogen bonding as long as there are other fluorines, oxygens, or nitrogens in solution. Okay, now, do you recall if hydrogen bonds are stronger or weaker than dipole-dipole interactions? Which one is stronger, hydrogen bonding or dipole-dipole interactions? Hydrogen bonding, right? So if we look at our methanol molecules dissolved in water, it's probably going to take more energy to break apart those hydrogen bonds versus just regular old dipole-dipole polar bonds, or intermolecular forces, I should say. Now, one thing that does come up is if you do have a really long carbon-hydrogen chain attached to your OH group. So for instance, down below, we have this really long hydrocarbon chain, and then we have our OH group at the very end. So the carbon-hydrogen chain, remember, has only van der Waals or London dispersion forces present. So this is a non-polar region. So this is insoluble in water. And then we have our polar region, which is the OH group, and that is soluble in water. So if you have a really large alkane attached to your OH group, then you have greater hydrophobic regions. So hydrophobic means fear of water. So those hydrophobic regions are going to want to point away from water, which means that they're less soluble in water. Now, if you do have an alcohol like this one down below, water will interact only with the OH group. So you can see that the hydrogen bonding only occurs on this very polar end. This is actually really similar to how soap works. So soap usually has a very hydrophobic section and then a hydrophilic section that loves water. And soap molecules will arrange themselves so that they have basically the water section pointing out, and then the hydrophobic section pointing, the hydrophilic section points out, the hydrophobic section points in, and basically this will surround any dirt particles or whatever you have on your hands, for instance, and then it carries it away when you wash your hands. So this little structure that soap forms is called a micelle. And it's very similar to how this alcohol is interacting with water down below. Okay, so let's talk about another property here. So if you do have more and more carbon and hydrogen atoms bonded to your alcohol, then that's going to make the solubility of your alcohol decrease. So for instance, on this graph, we have the number of carbon atoms in the molecule on the x-axis. On the y-axis, we have water solubility, and that's increasing going up. So let's look at 1-butanol. So that looks like the following. So there are 4 carbons on there, and this has actually a pretty good solubility in water. But let's add another carbon atom. So let's look at 1-pentanol. 1, 2, 3, 4. Oh man, I don't know if I can fit this. I'll just put the OH up here. So we added another carbon, and already the solubility has decreased quite a bit. And that's due to those non-polar interactions, and that non-polar section wants to get really far away from water. So it's going to be more difficult to dissolve this alcohol in water. Now, if we add even more carbons, you can see the solubility keeps decreasing as we go. Okay. Now, additionally, because of those OH groups that can hydrogen bond between alcohol molecules, we're actually going to see a really high increase in boiling point. So let's completely forget about water, and let's just say we have a sample of pure alcohol. So down below, we've got ethanol molecules, and that's all we have in solution. We don't have any water, nothing else. We can still see hydrogen bonding occur between each of these alcohol molecules in solution. And remember, hydrogen bonds are really, really strong compared to, for instance, dipole-dipole interactions. So the more hydrogen bonding you have, the higher the boiling point. Now, this can also be true for alcohols in water as well, because there is hydrogen bonding there too. So the more hydrogen bonding present in a solution, the higher the boiling point too. So on this chart, we have molecular weight on the x-axis. So really, molecular weight is just telling us how many atoms we have, essentially. So the higher the molecular weight, the more carbon and hydrogen atoms we have. And then the boiling point is on the y-axis, and that's increasing going up. So at the bottom here, we have alkanes. And you can see that the boiling point increases with molecular weight. Ethers are also in this section here, but we're going to ignore them for now because we haven't really talked about ethers yet. But ethers have really similar boiling points to alkanes. Now, way up above that are alcohols. So the boiling points for alcohols are much higher than the boiling points for alkanes. So let's just write that down. So the boiling point of an alcohol is greater than the boiling point of an alkane. And that's due to hydrogen bonding. So alcohols have H bonding, but alkanes don't. They just have those London dispersion or van der Waals forces, which are weaker forces. So can you guess what type of force ethers have? So if ethers have similar boiling points to alkanes, do we think that they have van der Waals forces or hydrogen bonding forces? Probably van der Waals forces, but we'll talk about that more later. Okay, so just something to keep in mind that alcohols have larger boiling points because they have those strong intermolecular forces in solution, whereas alkanes have lower boiling points because all they have are those really weak van der Waals forces. So it takes much more energy to break apart hydrogen bonding than it does van der Waals forces. So next time, we're going to go over alcohol reactions. So keep in mind the primary, secondary, and tertiary classifications that we went over because that will be important in the next lecture. So I will see you then.